Hi, everybody. So today we are going to continue on working through 2C and 2D. Last video we finished 2C, uh, as you can hopefully see as I scroll. No, I might need to scroll a little slower. So now we're on to worksheet 2D. Here we are going to start going over the formal definition of what a derivative actually is. So on P15, it asks us, so on the graph below is the function x equals 1/2 at squared. Use this graph to show the transformation from average velocity to instantaneous velocity. So what we'll do is we will use this to go over the traditional way to arrive at a limit, and it involves a limit. The traditional way to arrive at derivatives involving a limit. And I've also posted a Khan Academy video where they go into more detail than I will. So if my explanation doesn't make too much sense to you, go ahead and watch that Khan Academy video. It's about 15 minutes. That will help you as well. So if we want to find the average velocity between these 2 points, what we would do is we would draw a secant line. Let's draw a secant line right here. Oh, close. Secant line. Found out there's a ruler on this thing, so that's neat. Whoops. So if we wanted to find the average velocity between these 2 points in time, what we would do is we would find the slope of this secant line. However, we want to find instantaneous velocity. Say we want instantaneous velocity at this point. Okay. So what we would need to do is we would take this secant line and we would move ever so closer to this other point. Okay. Now, what I'm going to do to explain this is I'm going to completely restructure the whole problem just so that we can get a general definition instead of a specific definition for the function x equals 1/2 at squared. I am going to call this f of x. Okay, so this is just f of x. Here is x. Here is f of x. Okay. Now, we are going to say that this is at some point x, and this is at some point x plus any delta x. It doesn't matter what the delta x is, because this is going to work for any point on the entire function. But if you want to find the instantaneous velocity on something that's not a curve, then it's pretty easy. You just find the slope of the linear line, and you've got the instantaneous velocity throughout the entire graph, right? Because it is the slope from a position function. Now, if it's more complex than a curve, than a parabola, then you've got more work cut out for you. But this is how you can find the derivative or find the instantaneous velocity from a position graph. So what we will do is we will now label these guys. So this is the point. Actually, I'll start with this guy. This is a more simple point. This is the point x, f of x, right? Let's widen, bolden up that there. Okay. And this would be, now the x value of this point is x plus delta x. And the y value would be f of x plus delta x. Get that a little bit more, thicker. So these are the 2 points that we're dealing with, right? Now, usually when you want to find the slope, because we want the velocity from position graph, let's find the slope. So slope is rise over run, which we did before. Move this for you. So rise over run, which is the change in y over the change in x. Okay, so let's find what would be the change in y between these 2 points, right? So delta y would be the top minus the bottom, right? The higher point minus the lower point. So our delta y would be the f of x plus delta x, f of x plus delta x. Then you would subtract the other y value, which is f of x. Let me get that better so you can see that. F of x. Okay, so that is our rise in this problem for this entire curve. You can plug in any x and any delta x, and this could work. Now, for delta x, we want to take the further right, or the greater x value, and then we will subtract the lesser x value. So we have x plus delta x, and then we'll just subtract x. Okay. Now, so that would be the slope of between these 2 points, right? Between any 2 points on this curve. Now, that's an average velocity on this curve. So let me rewrite that where you can see it. Slope is f of x plus delta x minus f of x all over x plus delta x minus delta x. Okay. So that's the average velocity between these 2 points. Now, if we want the instantaneous velocity at this point, what we will need to do is we will need to get that other point closer and closer and closer. So we would need to get the secant slope here, secant slope here, secant slope here, and as we get closer and closer, we will eventually arrive at a tangent line. And once we get the slope of the tangent line, we'd be able to figure that out. Now, algebraically, not very easy to find the slope of that tangent line without taking the limit in this scenario. So let's say that we want to get this value, x plus delta x, as close as we can to x. So what you could do is you would take the limit as delta x approaches 0 of a simplified version of this slope. Now, on the denominator, you guys probably noticed that we have, oh, and you probably noticed that I made an error right there. You probably noticed that we have 2 x's here. We have x plus delta x minus x. So those x's can be eliminated. Now the limit from, as delta x approaches 0 of f of x plus delta x minus f of x all over delta x, that is how you can find the instantaneous velocity on this curve at this point. And if we're honest, since we kept it in general terms of f of x, x, and delta x, this could be done at any point all along that curve. So if we move our question down a little bit. This is actually the formal general definition of a derivative. The definition of a derivative, formally and all that fun stuff, is the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Now, and that is our formal definition. So, that is one way that you can find the derivative of any function if you are able to get those values, and if you're a fan of limits. If you're not a fan of limits, then I've got a surprise for you. What we can do instead is do the power rule, which we've done earlier in a different video, and I just glossed over it. But what we will do now is we will scoot on down right here. And on Q36, it says we don't want to have to draw tangents on graphs every time we are trying to find derivatives or an instantaneous slope. Using the formal definition of a derivative, we come up with a formula called the power rule that we can easily use to determine the derivative. Write that formula below. So, the formal definition of a derivative for the power rule. Say we have a function x. Here, let me get a new color. Say we have a function x to the n. Okay, if we were going to take the derivative, now there are different notations to use for a derivative. Newton and Leibniz both developed calculus at the same time, and they had their own way of writing things, so that kind of caused some controversy. So in math class, you will mostly use a Newton notation, which usually can also go with this limit. That would give you, if you take the derivative of a function, you can show that as f prime of x, which is what I used in the other video. Now in physics, we're going to use Leibniz notation more often because Leibniz notation is much more direct, and you can be more specific about what you're taking the derivative of. But we'll go into that later. But just for now, believe me. So to take the derivative of some x to the n, that is shown by d over dx. You take the derivative with respect to x of x to the n. That would be nx to the n minus 1 power. And that is the power rule. What that means is you take the exponent, bring that down and multiply it, and then you reduce your exponent by 1. Now, as a quick example, question 37 says, what is the derivative dx dt of the function x equals 3t cubed? Now, first, let's talk about dx dt. Up here, I didn't say dx dt, I just said d over dx. Now, this is not something you need mastered soon, but it's something that's nice to understand for physics. So in this scenario, what dx over dt means is you're taking the derivative of x with respect to t. And the variable on bottom is the variable that we will use the power rule for. So notice we had an x here, and that is the one we use the power rule for. We have a t here. Let's say that, you can, whoops, that's going to be too small for me to write. Oh, no, it's not, because I can zoom. Okay. So if we say this is dx, oh, that didn't make my pen any thinner, though. Dx over dt. Dt is the one on bottom, and t is the one that we are actually going to differentiate with respect to. So if we take 3t cubed d over dt, what we will do is we bring that exponent down. So you have 3 times 3t, and then you have to reduce your exponent by 1. So 3 minus 1 would be 2. This would give you 9t squared. That is how you can take the derivative of an individual variable, variable. So, and when you take the power rule of a function, you will use the power rule on each individual term. That's the word I wanted. You will take the derivative of each individual term and then combine them back into the function. So hopefully we have some examples, and if not, I'll make up an example on the spot. Don't worry. Let's erase that, get that out of the way. Now, 38. Earlier we did a slope of the slope graph. You could call this the derivative of the derivative. We say that this is the second derivative of the original function. That's what you would call that. So what you could do is you'd simply apply the power rule twice. Do this with the function from Q36. So if we take dx dt of x equals 9t squared, right? Then that would mean that we take the exponent and bring it down and multiply. So you have 2 times 9t, and then you subtract 1 from your exponent, 2 minus 1 being 1. So that would yield 18t. So that would be the double derivative of the original x. My notation's a little off there. So what you're doing is because we already have dx dt, this up here is dx dt. So what you're doing is you're taking dx dt of dx dt. You're taking the derivative of the derivative, right? So I believe, and sometimes I get the exponents mixed up on this, but that means that this is called d squared x over dt squared. And I believe that is the notation for a second derivative using Leibniz notation. Now, if we were using the Newton notation, like up top, this is your first derivative, then a second derivative is shown with 2 tally marks. So Newton's was simple in that way, but when we get into physics, sometimes simple is not enough because, for example, you have a function x equals 3t cubed. Sometimes we have more than one variable. So we need to know what variable are we taking the derivative of. And dx dt tells us that. Take the derivative of the function x with respect to the variable t. This up here, this does not tell you that. This just says take the derivative of the function, which is not helpful because sometimes there are more than one variable in the function. So we need to know what are we taking the derivative of. Okay. Okay, so that second derivative notation is right. D squared x over dt squared. Again, not super essential, and we'll work more on that as we get further and further along. So a few simple derivative rules. The derivative of a constant. If you had a constant, for example, x equals 3t cubed plus 7. The derivative of a constant, so if we took d over dx of 7, there is no x there, right? So if there is no variable with that term, then the derivative is 0. The term just goes away. So for example, above, when we had x equals 3t cubed plus 7, say we added that 7, the derivative would still be 9t squared because the 7 would disappear after we took the derivative. All right, number 2, the derivative of a constant times a function. So this is tricky. Let's say that we had dx dt of 3 times 4t squared minus 6t plus 3. Okay. So, sorry, I had to make that up on the spot. So let's say we have the derivative of a constant times a function. One way that you could take the derivative of that is called the chain rule, which we will go over later. Chain rule really isn't just a constant. Chain rule is more of a function within a function, but we'll do that later. If you have a constant times a function, what you'll do is you'll multiply the constant through and then take your derivative. So let's say that would be 12t squared minus 18t plus 9. Okay. And then if we take the derivative of that, you get 24t minus 18. Okay. Bring the 2 down. 2 times 12 is 24. Reduce the 2 to 1. And then you keep the subtraction sign, and you bring the 1 down from the t. 18 times 1 is 18. Subtract the 1 by 1 to get 0. So t to the 0, again, is 1. So then you have 18. And then the 9 just goes away. It's a constant. You don't take the derivative of a constant. I mean, you do. It's just 0. So the derivative of a summation or subtraction of functions. So let's say we have, this is going to be tricky to write. We've got f of x plus g of x, right? So the derivative of the summation or subtraction of functions, let's do summation first. So the derivative of the summation of functions is the same as the summation of the derivative of functions. So let's say coming up with notation on the spot is tricky. So let's say h of x equals f of x plus g of x. If we needed h prime of x, and sorry, I'm switching back and forth on notation, h prime of x would be the same as just taking f prime of x plus g prime of x. Okay. When we use these math definitions, I'll probably use Newton notation just for simplicity's sake, because Leibniz notation can get tricky when you have so many letters. But if you're taking the summation of functions and you want the derivative, just take the derivative of the functions and add them together. That one's not very tricky. Just like the constant times a function, not very tricky. You just multiply the constant through the function, then do your derivative. Here, you would take the derivative of each function, then add it together. And then that same could be said for subtraction. Let me see if I can scroll down. I cannot. Okay. So let's do this. So let's say h of x equals f of x minus g of x. Then, go. Okay, there we go. All right, so then h prime of x would equal f prime of x minus g prime of x. So if you're adding or subtracting functions, all you do is take the derivative of each function, then add them or subtract them, whichever was in the original function. Okay. Now, question 39, I don't have those videos loaded for what ASCII used, but what I did do is I added the Khan Academy video for the derivative of a function with the limit rule. I will see if I can find a nice and sweet video over the power rule too. If the video is too long, I won't upload it, but I will try and find a help video for you guys as well, just in case you guys need somebody else's voice other than mine. Right? But 2C and 2D, this was our part of our bridge of taking learning calculus and starting to apply that to the physics that we'll be using in class, kinematics, specifically position, velocity, and acceleration, and moving back and forth between the two using calculus.